Hi everyone, so today's topic is going to be comparing groups. And these are the things that we learned in the last lecture. In type 1 error, in type 2 error, we learned about alpha and beta and power, that is 1 minus beta, and Wiener's curse and effect size. I hope you remember everything. So today we are going to focus on the difference. And to know that, the important thing is to know the standard deviation of the difference. I'm going to use this as an example, the battery lifetime of brand name versus generic batteries, no brand. Battery lifetime of the brand name is like this, so that's minutes, and the generic batteries has these values. And if we make the box plot, you can see the brand name actually has a shorter duration. So we observed this difference between two groups, and what's the true difference for the general population? To know that, we need to know the standard deviation of a difference. We can say something about the population and sampling distribution, right? And there is a Pythagorean theorem of statistics, that is the variance of the sum or difference of two independent random variables is the sum of their variance. So like this. So variance x minus y, the variance of the difference is the variance of x plus variance of y. And that is basically the standard deviation of x minus y is the square root of standard deviation square, that is variance. So variance of x and plus variance of y. Okay. So this is the Pythagorean theorem of statistics, and this works only for independent random variables. Let's say there are two groups of proportions, and one standard deviation is this, and the other one is this. And the variance of p hat p1 and minus p2 hat equals should be this and this. It's simple. And standard deviation is going to be square root of that. And given that we don't know the p, population p and q, we are replacing this with the sample p and q. Okay, so it's easy. And to do that, there are assumptions. Mostly they are same with the previous lecture, previous slide. One additional thing, independent groups assumption. Usually this assumption is evident from the way the data were collected. For example, when you compare husbands with their wives, these two groups are not really independent, right? Or comparing subjects before and after some treatment, the groups are not independent. In these cases, we can use paired t-test that we are going to learn in the next lecture. Assuming the sampled values are independent and also the samples are independent and the sample sizes are large enough, the sampling distribution of P1 minus P2 can be modeled by a normal model with mu. Mu is P1 minus P2, and standard deviation is standard deviation of the difference of two groups, as we just saw in the previous slide. And the confidence interval should be the sample difference and plus minus critical value times margin of error. Here margin of error should be standard error. And here standard error is when we replace these population parameters with the sample statistics. And using this, we can do two sample G tests. Let's use this as an example, internet use before sleep. So 70%, 205 people among 293 of 19 to 29 years old versus 50.1%, that is 235 people among 469 people of 30 to 45 years old. So smaller proportion. And the null hypothesis is the proportions of two groups are not different. It's the same. So P1 minus P2 equals 0. That is null hypothesis. And the standard error should be calculated with this. It's easy. But so different from the confidence interval calculation, here we have the null hypothesis. That is P1 equals P2. So we need only one single value for P hat. So therefore we need to calculate the P hat again by pooling these two groups. So we can combine the counts to get the overall proportion. So that is P hat pooled, and that is basically we can get these, combine these two numbers and these two numbers. Okay, so in this case 205 plus 235 divided by 293 plus 469. So that is 0.5774, and the standard error of that is going to be using the P hat pooled and Q hat pooled. So it's like this, and then 0.0368. And z value can be calculated by subtracting the null hypothesis value from the p hat 1 and from the group 1 minus p hat from group 2 and divided that by standard error pooled. So that is 5.41, and that's quite large of z value, and that's the p value is less than 0.0001. We multiplied this p value by 2 because it's a two-tailed test. Okay, now let's talk about the means, confidence interval for means. To do that, we first need to know the standard deviation of the mean difference, and that's square root of variance of the sample mean of the group 1 and variance of the sample mean of group 2. And that's basically this. And standard error of this is going to be replacing this sigma with the sample standard deviation. So we can do two sample t interval, that is a sampling model based on students t distribution with adjusted degrees of freedom value. Because we are combining two groups, we need to adjust the degrees of freedom. So the degree of freedom equations are quite complicated, but you don't need to fully understand what's going on here. But when you do the analysis using the software, it'll automatically calculate the degree of freedom for you. Or you can look up this slide again, and then you can see the equation, and then you can calculate it. And you can do two sample t-test. The null hypothesis is going to be the difference between these two means is delta, and many times delta 0 is going to be 0. So the null hypothesis, there is no difference. So t value is going to be a difference minus delta 0 divided by the standard error of the difference. And standard error here is like this, and again degree of freedom for t value is going to be this. And then when the conditions are met and the null hypothesis is true, the statistic can be closely modeled by a student's t model with the number of degree of freedom adjusted. You can use this model to obtain p-value. Okay, so far we learned about confidence interval and z-test for the differences in proportions between two groups, and also we learned about confidence interval and also two sample t-test between two groups to compare means. And there are some distribution-free tests. One of the famous tests is Tukey's quick test. So this person came up with a simpler alternative to the two sample t-test. The important numbers is 7, 10, and 30. You need to calculate how many values in the high group are higher than all the values in the lower group. And also, you need to calculate how many values in the low group are lower than all the values of the higher group. And if there is a tie, there should be half. If the total number of n high plus n low is larger than 7, that is similar to alpha 0.05. And 10 and 13 gives us alpha 0.01 or 0.001 respectively. And this quick test is used sometimes, but not popular as a two sample t-test. So it was useful when we don't have any softwares, but now we have softwares and programming computers, so we are not using this many times. See this example? You can calculate the values that is higher than the largest number, that is 260, and there are 1, 2, 3, 4, 5, 6 numbers, and also there is one tie, 260, that is 0.5, so that's 6.5. And the lowest number of the group 1 is 255, and then there are 6 numbers that is smaller than the first group, so n low is 6, so therefore the sum is 12.5, thus p-value is between 0.01 and 0.001. And there is a rank sum test, and this is quite famous test, so Wilcoxon rank sum or Matt-Whitney test. It's less powerful than two sample t-test, but it doesn't depend on the nearly normal condition. So if you have any distribution that is different from normal distribution, you can use this. The procedure is like this: ranks the combined sample from the group together from smallest to largest, assign 1 to n. Here large n is the number of sample size of group 1 and sample size of group 2, so sum of that. If there are ties, use the average rank. And W, this number is important, is the rank sum of one group, and you can estimate the mean of W with this, and then variance of W with this. And using these two values, mean and variance, you can calculate the Z value. Let's use this example to understand this better. So let's say you have these values and you rank them across the groups. So you are having 130 and 175 and so on, and then you assign the number 1 to 14. And if there is a tie, you can say 8.5 and 8.5. So this is the same data set, and then just you rank them. And here red is one group and black is another group. Okay. So W is the sum of the ranks. So for the black, basically, so 250 and 50, that is 7 and 8.5 and 10.5, 10.5, 12, 14, 14, 14. All this sum of that is 90.5. And mu W is going to be because there is a N1 is 8. This is the mean, and variance will be this, using this equation. And then Z is W minus mu W divided by the standard deviation, and that is 3.7. From that we can calculate the p-value. Okay, there is a pooled t-test as well. So this is one type of two-sample t-test, but it's a little bit simpler than two-sample t-test. But it has a big assumption. The variances of two groups are the same. The advantage is this has a large degrees of freedom than two-sample t-test, and simpler formula for degrees of freedom. You saw that the degrees of freedom equation was really complicated in the previous slides, but here if we can pull two groups together, the degree of freedom gets simpler. So disadvantages are the assumption of equal variances is a strong one and is often not true and difficult to check. Okay, so the variance of pooled sample can be calculated with this. This is basically the weighted mean of the standard deviation or weighted mean of the variance, and therefore standard error pooled for the two groups is calculated with this. So S pooled from here, multiply that with this square root of 1 over n1 plus 1 over n2. So the degree of freedom is very simple, n1 plus n2 minus 2, and then we can calculate the p-value from that and confidence interval. Okay, so that's it for today's lecture, and don't forget to solve the quiz and check the summary. Bye, and see you in the class.